research directions for high-performance harvesting robots. Presented by Dr. Stavros Vougioukas, Professor and Vice Chair, Department of Biological and Agricultural Engineering at the University of California, Davis.
My name is Steve Brown. I'm the Associate Director of AIFS, AI Institute for Next Generation Food Systems, and welcome. First, to get going, I wanted to tell you a little bit about AIFS in case you're not aware of what AIFS does. AIFS is an institute that is funded by the U.S. Department of Agriculture, and specifically NIFA, the funding arm of USDA. And we have a vision of a healthier society and sustainable planet through robust food systems. And our mission is to develop and leverage transformative AI for the ethical production and distribution of safe, sustainable, and nutritious food with fewer resources. As an institute receiving federal funding, we have collaborators, sub-awardees, and they're over at Berkeley, Illinois, Cornell, UC A&R, and they have a group over at UC Davis as well, the Western Human Nutrition Center. AIFS has these programs ranging from farm to fork, essentially. And these are our maximizing impact areas of the food chain resiliency, infrastructure, and AI-driven food systems to improve human health. Anyway, so it's my pleasure to introduce Dr. Vougioukas. He received his diploma in electrical engineering from Greece at Aristotle University, and then a master's in electrical and computer engineering from SUNY Buffalo, and then a doctorate in robotics from Rensselaer Polytech. He joined UC Davis about 2012 and has since been a key figure in ag robotics. In fact, on a personal note, as far as AIFS goes, if anybody says what's going on in ag robotics, I mean, statewide, nationwide, this is the gentleman who is mentioned, one of the first people that gets mentioned. So we are very honored to have Dr. Stavros Vougioukas talk today. Welcome.
Well, thank you very much, Steve, for the kind introduction and invitation to speak today. And thank you all for being here. And everybody who is viewing on Zoom or who will view later, maybe with a cup of coffee or a glass of wine, whatever that is. So I would like to present today some thoughts about what possible research directions are to achieve high performance harvesting robots. And so this is a statement that doesn't come as a surprise to most students in Davis, where we're familiar with agriculture, but sometimes it comes as a surprise to other people. People think everything is harvested mechanically, but pretty much all fresh market fruits and vegetables are harvested by hand. And just to give you an idea of what that means, worldwide we harvest about 4.4 billion strawberries per year and 4.7 billion apples worldwide. So this is just two crops. So you can imagine 10 billion times a human hand goes out and picks something. Okay, so clearly that's a big thing. Now, the challenge is that farm labor has been diminishing, not only in the US, where you can see a graph there that shows that H-2A visas, these are visas for temporary farm workers, have been increasing steadily over time, but also the cost of that employment is going up. It costs a grower about $32 per hour to have an H-2A worker work on their fields. This is not what the worker is making. They're making $16 per hour or more if they're paid piece rate. But you can see the cost is really high, and we can't find enough people. And somebody might say, well, this is an American problem, you have this problem. Well, it's not only the US. China has it, Latin America has it, Europe has it, New Zealand, Australia. It's more of an issue with urbanization, that younger people want to be in a large city, enjoy the delights and experiences of a large city, even if they have to deliver pizzas rather than work in the fields. And there are also other reasons in different countries, but the bottom line is we don't have enough farm workers, and the ones we have are older and they cost us more. So what's the obvious answer? Replace them, have machines do the picking. Well, if you Google robotic fruit harvester, you will see a lot of articles, thousands of them, lots of pictures of robots harvesting fruits or vegetables. But the thing is that if you go out and try to buy one for your farm, none is available. You can't buy such a robot. And the question is, why aren't they commercial yet? Well, first of all, robotics is not a new idea for harvesting. The very first ones were done in the 70s, late 70s. Black and white camera, robot arm in a lab going after an artificial apple. To the left is an image, a picture from the PhD thesis of Professor Slaughter. He's retired now. This was in Florida in '85. And to the right is a wonderful machine by Advanced Farm, a company local in Davis, a machine with 6 arms harvesting apples. This is very recent, but still, this machine is a prototype. You can't really buy it. It's still under development. So why is it so difficult? Well, the answer is that it's not difficult to build a robot to harvest fruit. The difficulty lies in building a cost-effective robot, one that is practical, that makes sense to deploy on the farm. So what does that actually mean? Well, there are 2 major performance metrics that contribute to the cost of harvesting. One is fruit picking efficiency. So if you imagine there are 100 marketable fruits on a tree, if your harvester goes through and manages to pick 90 of them, and by picking I mean they're successfully placed in a bin to be carried away and they're not bruised or damaged in any way, then your efficiency is 90%. If the robot can only do that for 60 out of 100 apples or orange or whatever, then your efficiency is 60%. Clearly, the higher the efficiency, the better. If the robot leaves half of the fruit back and that fruit goes to spoil, it doesn't make any sense. The cost is very high. The other metric is that it has to do with speed. We can call it fruit picking. How many fruits per second can you pick? Or how many seconds it takes to pick one fruit. Some people may argue, we have 24 hours in a day, even if the robot is slow, it's fine. It can work day and night. Well, that's not really the way things work, because harvesting doesn't work in a vacuum. There is a whole chain of people supporting the harvesting, operators, workers. There is a supply chain. You have to haul the fruit away, take it to a shed, do packing, etc. All of these would need to work 24 hours a day to support such a thing, a robot operating 24 hours a day. Also, harvesting windows are short. You may only have 1 week or 5 days or 2 days to harvest a field. So would you deploy 200 of these robots because one is very slow? What about logistics and cost? So the answer is that we want to have fast robots and efficient robots. Otherwise, they don't make sense. So let's dive into the details of what does it mean to have an efficient robot. What does efficiency mean? Well, think of going with a machine in front of a tree, for example, and using your cameras to acquire images so that you can find all the fruit. Well, if there are 100 fruits on that tree, only a percentage of those will be visible through the cameras. So let's say that's 90 or 80 or 60%. Now, out of those visible fruits, only 1% will be detected by your super duper AI, neural network that's doing classification and localizes the fruit. It's not going to be 100% for sure. And we also know, people have studied the fact that the lower the visibility of the fruits. So if the fruits are occluded 90% or 80% or 10%, then the confidence of detection goes down. So the higher the occlusion, the lower the confidence, and that essentially tells us that you would like to have high visibility and high detectability perception. But that's not the end of the story. Let's say now you have the coordinates of fruits on the tree. How many can you reach? What's the percentage of fruits that you can reach? Perhaps your arm is not long enough to reach all of them. Perhaps there are wires or other things in front of the fruit that don't allow the arm or the gripper to grab the fruit, as is the case in this situation. So only a percentage will be reached, and then after the arm reaches the fruit, only a percentage of those fruits will be successfully detached. Some of them may drop, and you can't really grab them, or some you may squeeze too hard and damage them. And so these are just examples of a gripper going after a fruit, but it can't detach it. Why? It missed it, or there was leaves in front of it. These are all contributors to the percentage that doesn't get detached. And then after you detach those fruits, another percentage will be successfully conveyed, because you have a fruit in your gripper, now it needs to be transported to a bin. So there's a conveyance system. And through that system, as it travels, it may get bruised. And so that means that only a percentage will successfully make it to the bin. Now, what's the efficiency? Clearly, it is the product of all of those intermediate efficiencies. And we all know from basic math that if you multiply numbers smaller than 1, the end result cannot be 1 or higher than 1, or it can only be smaller than 1. Here's an example. You have a great AI system doing perception. It finds 98% of the fruit in an image, but you only see 80% of that fruit. And then you got 95% reach, 98% detached, 99%. So everything looks great, but one of those links in the chain is weak. And the weak link is the visibility. And now you have a 72% efficiency. So 28 fruits are gone. They're not in your bin. Maybe they're on the floor, maybe they're still on the tree, you didn't pick them. So that is a problem that increases the maybe you need more people to come and harvest the rest of the fruit.
So the percentage visible, this is for RGB kind of vision that we capture?
Yes. I'm talking about RGB images or RGBD images. How good do humans do? Well, are people efficient? The truth is that we don't have exact numbers on worker efficiency, but from the observations that we have done, people are about 90 to 95% efficient. When you see workers go through an orchard block, and then if you go and see how many fruits are there, they pretty much strip everything down. They're pretty good at it. So their efficiencies are very, very high. Now, what about robot efficiencies, where it goes all over the range, anywhere from 90% in some publications, but usually these are small-scale experiments, to down to 40%. And so that range really varies depending on the machine and what people choose to report. Now, let's talk about speed. So speed has to do with the peak cycle, how many seconds it takes to grab a fruit and put it into the bin. Well, let's assume that you have targeted a specific fruit and it's circled with a yellow circle. Now, it will take some time for that arm to position the gripper close to the fruit so that it can start the detachment motion. And then it will take some time to reach out to the fruit. It will take some time to actually detach the fruit from the tree. And it will take some time to transport that fruit from the gripper to the conveyance system, whether it's a conveyor belt or some vacuum system. And all of those times need to be added together to give you the full cycle time. And so how fast are now people and how fast are now robots? Well, this is a video courtesy of Advanced Farm. Uh, Two arms are picking approximately, or take approximately 3.6 seconds to pick a fruit. This is two arms. It's pretty good. It's pretty good. Single worker on the platform with two arms takes about 2 seconds to pick one fruit. So what we see is that a machine with two arms is a little bit slower than a person with two arms. Uh, so that gives you an idea. Now, if the machine though costs $250,000 and it has two arms, it doesn't make sense. If it has 6 arms, of course, then it can be 3 times as fast. So you can start seeing that one machine must replace many people in order to justify its existence. Strawberries, this is another video from Advanced Farm. It's about 2.4 seconds per berry without packing them in clamshells. A worker takes about 1.6 seconds per berry with packing. So strawberry pickers are really, really fast. They're faster than machines. Now, how do pickers harvest? Why are they so fast? How can they do it? Well, what people do is basically they use their eyes to see, to sense, right? And then based on that visual information, they position themselves close to the plant. And then they also use their eyes to find targets to pick, so they reach out. Sometimes they may push the canopy, the leaves, or other fruits to get to their target. They also move very fast, they don't go slow. And then they use again their eyes to detach the fruit from the plant. And then they may actually have a fruit in their hand and go to grab another fruit with the same hand. So they can grab 2 or maybe 3 fruits with one hand. And then after they do that, they transport it to their picking bag or their clamshell container. And then they go back and reposition themselves to another plant, and they keep doing that very quickly. So this is the cycle of what a human does in order to pick. Now the interesting thing is that if you observe them, sometimes when they reach a fruit, they're not actually looking at it directly because they already spotted it when they picked another one nearby. And so they may be looking away to pick a fruit while grabbing the fruit that they already spotted. Also, when they detach, it's not necessary that they always are looking or paying attention to the fruit that they're actually detaching. So their sensing, their vision, and their action are not always coupled together. And so that creates a question like, how is that done? And the same for transport. When they put an apple into their bag, they don't need to see the apple as it goes in, they just put it in. And what I'm saying is not something new. We already know that people create mental models of space, and actually they even have mental models of physics. So a picker will know that a fruit is there, and they may even know that there is a branch there in front of it, and they will just do a motion to get that fruit without even looking at it. So the thing is that they're using a combination of direct sensing, but also a model that they have of what's in front of them in order to pick. And how they build this model, they actually build it by active viewing. So they're looking, but also as they pick one fruit, they look nearby to find their next targets. And as they do that, they build this model inside their brain. And also that model helps them look at other viewpoints in order to essentially discover more fruit. And the more experienced the picker is, the better they do this. This is a video from a professional strawberry picker. We actually put glasses on them with a camera in the front. And so we wanted to study how they pick, what they're looking at. And you can see that this is 10 times slower than what they actually do in order to have time to see what's going on. But if you observe this video frame sequence, you will see that their hands and the direction of the camera is not always aligned. Sometimes there is a peeking action and they're looking at something else. So basically what I described before, that people don't really need to be sensing and acting in a closed, tight loop all the time. They use internal representations of what they need to do, what's in front of them. So moving forward, our ultimate goal is to achieve superhuman speed. So any machine that costs $500,000 should peak many times faster than a person, not just one person. And then we also want to achieve human level efficiency. So we want to match the perception of human peakers. Now, we need to keep in mind that we don't really need to build machines that replicate humans or the way they do things. We can do it differently. Humans have two arms that are articulated. We don't need to do that. We could pick in different ways. We don't need fingers, perhaps. But overall, the goals are high superhuman throughput and human equivalent perception. The other thing is that picking efficiency and speed are fighting each other. If you want to have perfect, non-bruised fruit, you harvest them very slowly and delicately. If you want to have high speed, you go and do very fast motions. If you are very fast, the damage will increase. If you are very delicate, then the quality will increase, but the speed will decrease. So there's a little bit of a trade-off there. Now, how can we possibly proceed towards human-like efficiency? Well, this is the figure that I showed before. So we definitely need to do some to have advances in the sensing part of the robots, in the modeling and how we build some representations of what is in front of us, and also the sensor and model-based actuation. This is not just a closed loop visual servoing, there's a camera and an arm and it's speaking. It's the combination of using a camera but also using an internal representation to do the action. So we need to advance in all of these areas. And one way to advance in sensing is to build active vision systems. This is from a recent paper and a video where a robot arm is actually trying to select the best views in order to discover more fruit or to increase the visibility of specific fruits. So this has already been done, it's not something new, but in our case, for harvesting robots, we need to do active sensing without sacrificing the picking action. So if you have a gripper or an arm and a gripper that harvests, you don't really want to delay it by active sensing. So you want active perception, but not really use your arms that are picking to do perception. And so possibilities exist that you could use multiple fixed cameras. You might have other arms that only do perception, not picking. You might have little UAVs with cameras flying around and discovering where the fruits are. You might have cameras on your picking arms that discover more data, that get more images. But the bottom line is that we need to have active vision, and that active vision should not interfere with the action. We don't want to slow down the machine. The other thing is modeling. So how do we build representations of what's in front of us? In graphics, visualization, in robotics, the conventional approach is that we represent objects either as triangular or surface meshes or point clouds or voxels. Voxels are very common. I have an example here. The idea is just like a screen is split into square pixels, 3D space is partitioned into 3D cubes. And each cube can be occupied or not occupied by an object and have some optical properties. And if you use that idea, you can represent any object using these voxels. This may remind you of familiar video games where there's worlds comprising voxels. And depending on how many voxels you use, the level of the representation can be finer, can be better. This is all done. We already use it a lot in robotics and graphics and visualization. The problem with these representations is that if you don't have enough viewpoints to build them, they have holes in them. They cannot represent well the space, and also they cannot generalize or interpolate to give you views of the world that you haven't really seen yet. So this is an example of a 3D space. It's not an orchard, of course, it's an office space, but you can see that as you rotate the viewpoint, there are lots of holes here because you've never seen the chair from the side, so that part of the chair is empty, there is nothing there. But people are able to imagine in their heads how a chair would look like or how any object would look like if you rotate it. I'm not as good in that, some people are better. Artists, painters are very good at that. And so we need representations that can create novel views of what has not been seen before in order to use those for harvesting. And so there are various approaches right now. One idea is instead of using cubes, voxels, to actually use little ellipsoids, smaller, bigger ellipsoids with certain optical properties. These are called Gaussian ellipsoids. And the idea here is that these can actually do more interpolation and better representation of your space. So this is still an explicit representation. And this is a short video of a plant being represented by such Gaussian spheres or ellipsoids. Another approach is using neural networks. This is a different approach where you essentially take images of a scene and then you train a neural network to implicitly represent that space in terms of geometry and optical characteristics. And so this is an example of a plant that has been, images of the plant have been taken and they have trained a neural network, and then you can generate a movie going around that plant, but you're not really using a camera. The plant, the representation of the geometry and the looks of the plant are embedded in a neural net, and then that neural net is used to render the plant. So this is another approach that we could use to create these models for robotic harvesters. Such nerves, neural radiance models, have been used for agriculture. They can be trained, some versions of them can be trained quickly in real time, and they can also be used to combine them with robotic action. So there's much more to be done, of course, right? So these are just preliminary ideas, things that have been done also in other areas. But the bottom line is that we need to be able to create and dynamically update models of the canopy in front of the robot. Why? Because we want to use the cameras, the real-time sensing, but also our knowledge, our model of that space where the fruits are, the wires, the twigs, the leaves, etc., in order to guide the robotic actions. So, how do we guide the robotic actions? Again, there's two approaches. One is conventional. There's motion planning algorithms that compute the geometry of things and so that the arm can go around or go and pick without hitting things. But there is also AI-based approaches where you teach a robot arm how to move and grasp, say, a fruit or fruits based on data and the mental models that the representation we talk about. Okay, what about throughput? We talked about perception and the need to create more rich models that we can use. What about speed? Well, we said that if you have one arm, if it's very fast, it probably will cause damage. But if it's very slow, the machine will be very slow, right? And so one idea is to, okay, use one arm that doesn't move very quickly. It's slow. And it's slow, that means also it's low cost, it's not very expensive. And also if programmed well, it doesn't damage the fruit that it picks, okay? But then once you have this nice, slow, cheap arm that can increase your efficiency, then you utilize a large or very large number of those arms in order to increase the throughput. So the combination of one low-cost, slow arm, but then deploying many of them to address the speed issue. So we have been working for the past years on a USDA NIFA project where the goal was to study how you can build such machines with many arms and how you can program them. Because imagine if you had 20 arms on you and you were about to pick apples. What arm does what? How do you control the arms? You know, as you move and pick, maybe the arms in the front are picking a lot, and they're picking everything, and the arms in the back are idle. They have nothing to pick. So unless you load balance the work and program those arms carefully, they will be underutilized or even idle. So the theoretical question was, how can you program them to have a linear speed up? 5 arms are 5 times faster than 1 arm. 20 arms are 20 times faster, and not just a plateau. And so our approach was to build arms that are very simple. They're linear, up and down, in and out, left and right, and they're configured in some kind of array. And then as the machine moves, we perform planning of which arm harvests which fruit, when, and then so we first build a map of where the fruits are using a camera or more cameras. So now we have fruit coordinates in front of the machine. And then we use those coordinates to solve the problem, how fast can I move, which arm picks what, when should each arm move. And then execute those harvest motions and then go back to step 1 to update your map of the fruits and keep doing that. Now, the machine is being built, so we don't have the full thing, although we have a prototype in the lab that's actually, the arms are moving. But we have work done that's more theoretical that try to solve the theoretical problem of, if I know the coordinates of the fruits where they are, how do I program arms to harvest them? And so what I'm showing here is an example from a simulation where there is a number of fruits here, and there is a large number of arms picking all those fruits. And what we see here is that the front arms are not picking everything. They're picking enough, but they leave enough fruit for the middle arms and enough fruit for the rear arms. Mm-hmm. So they're not just opportunistic, let's find something and pick it. They're actually doing something smart. This was solved, this is a numerical optimization problem that is extremely complex, but it was solved using heuristics in less than a minute, so it's pretty fast. Of course, the heuristics work because the arms are pretty simple. They're linear, like I said. What about the performance? Well, this shows you what we have achieved, or the PhD student who did the work actually achieved. When you have one arm, it's about 1/3 of the speed of a human, so it's a slow arm. But if you have 40 arms, you achieve 10 times human performance. So you can envision a machine with 20 arms left and 20 to the right, picking through an orchard. It's replacing 10 people. Now that makes sense. If the machine replaces 1 or 2 people, I'm not sure if it makes sense. So are we done? Well, we are not done. First of all, this is simulation and theoretical, but it shows what could be accomplished. But what we still need to do is, what if you use articulated arms? arms that have more degrees of freedom so they can reach deeper into the canopy and get more food, etc. How do you solve this computationally difficult problem of planning the assignment of arm to fruit and when each arm should move and how it should move? It's a really complicated problem to solve in real time. And so there is different approaches. One is to use some kind of numerical optimization heuristics and use GPUs or CPUs to solve it. Another approach is to again parallelize for learning, but use reinforcement learning type of approaches. And this is like just a video from NVIDIA where they're using robotic simulation, but they're spawning it on hundreds and hundreds of cores, and they're teaching a robot to do certain motions, certain actions by exploiting parallelization and reinforcement learning. So these are again two different approaches, but we will need to move in this direction to achieve this superhuman speed for complex arms. So the take-home message from the presentation is that we really want cost-effective robots, and to have cost-effective robots, they need to have superhuman speed and human-like perception and efficiency. And so we envision that these robots will have a large number of arms that are going to be low cost. Each arm will be low cost, and they have to be well coordinated to achieve that superhuman throughput. Also, we want to use, or we propose to use, many sources of imagery, of sensing, of RGB or RGBD images, in order to create those representations of what's in front of us, those models or mental models, if you will, that the robot can use to improve its picking action and increase the visibility, of course, of the fruit. And then we want to use those models to control the arms, but also the sensors to control the arms. Now, AI is a big part of all of these approaches. Not necessarily everything is AI. I mean, the example I showed before with the arms picking, that was numerical optimization and heuristics. So it didn't involve really AI, but it was also for simpler arms. When we move to more complex arms, we may need to go into other approaches. And by that, I would like to thank you all for being here. Of course, I get to talk about this work, but others are actually the ones who do the work. And so the names and faces are here. And I would also like to thank AIFS and, of course, USDA NIFA for support, and growers that helped us with experiments, and Advanced Farm for giving images and videos, and for being so open with the results and data. Not every company is like that, so we really thank you.
Any questions for Dr. Vougioukas, please feel free to ask, and if you could go ahead and repeat the question for the Zoom feed as well. Anybody?
Can the perception be improved if we change the kind of cameras that we are using?
So the question was, can the perception be improved by changing the cameras we use? The answer is very likely yes. And so there are different modalities of sensing, terahertz imaging, phased arrays of ultrasonics that can be used to even discover things behind foliage, possibly, multispectral imaging. So what I described refers to RGB images, but some of those models, like nerves, for example, have been applied to ultrasonics. They have been applied to other sensors. And so I definitely do not exclude other sensing modalities, but I use the images because this is what we are using now. But this is a great question. We should also think out of the box when possible and explore other modalities for sensing.
I'm just curious, it's might be a bad question, but can you sense the tree as it's developing, like throughout the season, and then take multiple images, keep taking images, so like the robot gathered a lot of data and has an understanding of how the tree developed and exactly where the fruit was and its positions. So it's not like seeing it first time when it's harvesting, but it's kind of like built this.
That's a good question. Actually, people have tried that to essentially image the tree before even the foliage is there. And so you have an a priori information about the structure, the geometry, you know where limbs are. That can be done up to a point. But imagine a tree limb full of fruit. Actually, that limb is deformed because of the weight of the fruit. And as you harvest one or two of them, it's being deformed again because there is less weight. So there is a limit to what you can do, and you can do that, but maybe for basic obstacle avoidance. But it's difficult to use such information for harvesting in the real world. There's a limit to what you can do. Yes.
I had a similar question. So, like, maybe instead of doing it over time, separating the steps, like maybe have a robot to just go around the tree or all the trees and kind of build maybe like a nerf model to understand where the fruit is, and then have a separate robot come in and pick them just because it knows where they are now. So instead of that situation where you look for it and pick it, you just look for all of them, kind of place them on a 3D model and then pick them later. Is that something that seems also feasible, or is the
in theory, it might be. The problem is, again, what you are imaging in a first pass is dynamic. So as soon as you start picking, those fruits are moving. That's one issue. The other issue is the accuracy. So if you have a mobile robot that moves in a row and maps things, how accurate that will be, and when the second robot comes, if you tell that robot, hey, go to XYZ to pick an apple, is that apple still there? Or within 2 centimeters, 5 centimeters? So accuracy is also a challenge. The other thing is, what would you gain? That you may have more time to process those images to develop the model, right?
Yeah.
But how would that work? You would have to have then terabytes of imaging somehow uploaded to a farm computer, because forget the cloud, these are possibly terabytes. And then from that, it's crunching overnight to develop some kind of representation that will fit to a robot. The scale of that is really huge. And so, do you gain something? I'm not sure. People have tried, but mostly in simulation, not really in reality. Even when you have the camera in front of the arms, let's say 1 or 2 meters in the front, and you map, it doesn't mean that the coordinates of the fruits you found and you feed to the arms are exact. That's why you need to do also visual servoing when you go and grab the fruit. You need to use the camera in our robots to overcome that uncertainty that is coming from your imaging, from your GPS, from your odometry, from your localization overall. So in theory it works, but not in reality.
You touched on this a little bit in your talk, but I'm just wondering if you could give some more detail about some of the specific approaches researchers are taking for developing scheduling algorithms for many armed robots with more complex articulating arms.
Yes, so there isn't much work on coordinating a lot of arms that are articulated. But there has been a lot of work on motion planning for articulated arms that's almost real-time or real-time, so it's very fast. That's one thing. There has also been a lot of work done on scheduling and task assignment of multiple agents. And there has been a lot of work also on combining the two, primarily for flying drones, where it's a little bit simpler. And the approaches they range anywhere from casting the problem as a numerical optimization problem using integer optimization or mixed integer optimization. So mathematics, and solving those problems, but this is offline, you can't really solve it in real time. Some of these approaches are AI-based or algorithmic. Let's say these agents have an auction, who is going to do what, and then somehow they converge to a solution. Some other ideas are simple policies that assign based on which arm is busier, which arm is not as busy, how much load is coming in. And there is a lot of interaction in that field and in any type of multi-agent scheduling. So in factory floors, fabrication shops, even computation, web services, you always have limited resources and a lot of requests for jobs, and then you have to schedule that. In robotics, that couples with the complexity of actually assigning tasks that you have to make sure will not result in collisions of those arms. So again, numerical approaches, algorithmic, AI-based, lots of different approaches. I think the gentleman.
Yeah, I'm curious if with something like nerve, was a much better performance observed compared to just normal camera, which was an RGB2D?
If better performance has been observed with nerves versus a camera, nobody has tried it yet. We haven't really done. We haven't compared, camera-based control versus a mental nerve type of model-based control. They have been used for localization and SLAM in robotics, but not in this context. So that's something that we would like to do at some point. Yes, you have a question.
Me?
Yes.
I was just going to ask, are you guys attempting to combine these methods, or do you have to essentially just choose one? Like, will you have to choose algorithmic or numerical, or could you essentially use like that numerical work to inform that all?
The answer is whatever it takes.
Right. Okay.
Why be dogmatic? I mean, you could combine, but essentially we're exploring, or people are exploring different avenues and maybe combinations of those. But you shouldn't be dogmatic about it. Yeah.
A lot of the robots that you've shown, they're kind of standalone robots where they do the sensing and the picking. What about co-robotics, where you've got humans? For example, what if you had a human sensing just before the pickers, essentially standing in front of the platform? Humans are really good at that, and maybe using eye tracking or laser pointing or something else. They can say, okay, here are all the fruits. Now, arms, go ahead and pick.
In theory, something like that could be tried, right? But the devil is in the details. So, first of all, employing people to sit there and somehow find apples or fruits, they can't just stand there. A lot of it is active perception. So they would need to go in and look for things. Then they need to mark them somehow. And so a laser pointer means that they have to keep pointing at that fruit until a camera or a robot looks at it and registers it. And so that would delay them from discovering other fruits. Also the interface, the user interface of how do they do that, especially if their arms are picking fast, how would that work? Would it be fast enough? It's really, it's a concept that I'm not sure if it would work in practice. For sure, people are very good at finding things and finding fruit. And we could achieve human-level perception with humans. but whether those humans can seamlessly and cost-effectively collaborate with picking arms, that I haven't seen people do that. In other contexts, it has been tried, but it's not a context of fast operations like harvesting. It's different contexts. Yes.
So if you're modeling with nerves, do you experience some kind of a sim-to-real gap when you're using it in actual plants to pick up fruits?
Well, first of all, we haven't tried it yet, but some people have tried modeling plants with nerves, and they're using actual images from plants. And so then when you render those plants from a different viewpoint, they look pretty realistic. And you can also take a real image from that viewpoint and compare the two. And so people have done that. I can't give you error metrics, but they can be very, very good depending on the quality of the input images, how many you have, the structure from motion quality or the pose uncertainty in those images. But they can be very, very accurate. Now, we haven't tried that for our system, but this is something we would like to explore.
I'll ask one. We have some other groups within AIFS doing some work, and one area is just spotting the fruit, identifying it. We've seen grape identification. This is a cluster. This is an apple. What to you is one of the best developed areas that you would say that this is how we can move forward quickly? How can we recognize this? Is it fruit? Is it apples?
So actually, our group now within AIFS involves also Mason Ayers and Brian Bailey. We are looking into using the synthetic images or the simulator that has been developed by Professor Bailey to train such systems and try to evaluate these approaches using a virtual environment. And so the hope is that we can more quickly explore whether something can improve things or it cannot, or what combinations of approaches can improve the situation. So what the virtual environment will give us is the possibility, the capability to explore different approaches and also quantify how good are they, because we have ground truth. They're synthetic orchards, and so we know exactly where the fruits are, where the leaves are, where the branches are, etc. So this is something that's being done now within AIFS with collaboration from multiple people.
Nice. That is Helios.
Yes,
project
correct.
From Dr. York. Any other questions?
How long do you think until fruits are being picked apart by robotic?
To be honest, that was the last sentence of the slide. I took it out because if I try to be a prophet, I would be a fool. People will come back and say, "You said that." But if you ask a startup, it's 2 years down the road, right? Autonomous cars were 2 years down the road. It's not happening overnight. I would say perhaps 10 years or something. Not because it's not possible, but things take time. Even if tomorrow we had a robotic harvester that's super efficient, etc., you need a support network of dealers, of marketing, sales, support. You need adoption by the growers. You need a good business model. These things take years. When the tomato harvester was invented here in Davis, in our department, and also with collaboration with plant sciences back in the 60s, it took probably 8 years or so from the first prototype to actually this widespread adoption of the machine. The machine was working, but it was being improved, becoming faster, etc. So technology takes time, especially in agriculture. It's not a factory floor. We don't control many things. So it takes years. Hopefully the companies that are doing a great job developing this technology, and they will have the VC or investor funding for the foreseeable future to actually get those products out in the market. The need is there. So I think it will happen, but it's not going to happen in a couple of years, or at least at a larger scale.
All right, we have time for 1 or 0 more questions. Any more? All right, thank you, Dr. Vougioukas.
Thank you.